Hey guys, these are your notes on what's called the coefficient of friction. So watch them, write them down, and listen as I go through them. The coefficient of friction, it's a variable with a Greek letter mu. It looks like a U with a long tail in front. You might know the Pokemon called Mew or Mewtwo, is named after that Greek letter. And that letter stands for the coefficient of friction. What is the coefficient of friction? It's a rating of friction based only on the pair of surfaces in contact. So it rates, say if you have two really rough surfaces or grabby kind of surfaces, that means you have a high coefficient of friction. If the surfaces are slippery, then it's a low coefficient of friction. It just rates it based on the actual materials that are in contact. We know friction can also change. The force of friction can change based on the weight of the object. A refrigerator has much more friction applied to it than a chair. So the coefficient of friction, it's not based on the weight of an object. So if you put the slippery things on the bottom of a fridge, then you've improved the coefficient of friction if you lowered it, right? But it still has a lot of friction on it because it's heavy, right? So it's not based on the weight, simply based on materials. Mu always has a rating of 0 to 1. It's always a decimal. Alright, so 0.1, 0.2, all the way up to 0.9 something. Sometimes it's 1 point a little bit, but not too much over 1 if it ever goes over 1. It's always a positive number as well. It has a formula. Here's the equation to calculate mu. If you know the force of friction, there's your equation. If you know the force of friction, you know the normal force applied to an object. Mu is the ratio of friction force to normal force. And the unit for mu, well, if you know both forces have units newtons, and you divide newtons by newtons, what do you get? Well, they just cancel out. So the unit is, there's no unit. It's unitless. It's just a rating, so it's kind of unitless. Examples of different coefficients of friction. A very low coefficient of friction. Originally, the lowest discovered was 0.04. Teflon on Teflon. So Teflon, what is Teflon? It's what your nonstick pans are made of. So it was discovered by accident in a lab at Georgia Tech, and they figured, wow, what the heck is this stuff? It's really slippery though, and they measured its coefficient of friction, which you're going to do to other surfaces later on in the week. And they figured out that, wow, this stuff, it's also, safe to put on surfaces to eat off of, and it's going to be perfect for a nonstick pan, completely discovered by accident. We've pushed the limits as far as slipperiness even further with where there's a lot of money or prestige at stake. In speed skating, is where a lot of slippery materials are desired. So speed skates on ice gets you a little bit of a lower coefficient, just 0.03. That's the lowest to date. Rubber on wet asphalt, 0.25. Rubber on dry asphalt, 0.9. Big difference, right? On how much friction you could get based on whether the road is wet or dry. Much more on dry asphalt. A couple of years ago, another good example of coefficient of friction. A couple of years ago, my students sent me this picture when they were out running. They're like, oh, we're doing coefficient of friction in class, and they said, let me take a picture of this and show Kabbalah, because it just reminded me of it. If you've ever seen the red roads, especially around turns, what's the point of that? Well, on a turn, you need more friction to keep from kind of sliding off the road, especially on a turn that kind of goes downhill as well. And the point of the red roads is it's a material different than asphalt that increases your coefficient of friction to give you more friction. Alright, so we could rearrange this definition of mu to make a friction equation. Let's do that. Let's multiply both sides by normal force and write this down for yourself. Cancels on the right. And we get force of friction equals mu times the normal force. That's another way to write that. Alright? So if you want to calculate force of friction, you got mu and the normal force, just multiply them together and you get the force of friction. So really there's two ways to change the amount of friction on an object, FF. FF is the amount of friction. There is the materials, and it's always the pair of materials. You could change the top material or the bottom material. Or you could change the normal force. If you increase Fn, friction will go up, and if you increase mu, friction will go up. So let's look at changing friction by Fn. Let's look at an example of like a truck on a snowy day. You know, a snowy day is where you're always thinking about how can I get more friction. So draw yourself a little pickup truck here. I'm going to draw so you can see what's in the cab there. We'll call it a pickup truck, right? Lift that up a little bit. So you could get more friction on a snowy day by changing the normal force applied to the truck, right? So say I don't want to slip on the road, I want to make sure I'm good. What you're going to do is if you add a couple concrete blocks right there, so add concrete to the truck bed. What you're doing is you're increasing the weight of the truck. So what we did is we went from an FG like that without the concrete, and we add the concrete. Now we have a higher weight. So what we did when we added the concrete, to balance out that weight, there's going to have to be a greater what? Without the concrete, the truck didn't need much normal force pressing up on it. But if you add weight to the truck also needs a greater normal force pressing up on it from the ground. So the ground needs to support it using more force when there's concrete in it. So by increasing the weight of the concrete, we also increase Fn. And you know, when we increase Fn, when we make that larger, we also make friction larger. When Fn goes up, friction goes up as well. So that's one way, you know, I could say like, well, who would have a greater force of friction, Shaq or Kobe? Well, Shaq, because he has a bigger Fn applied to him, because he's just a bigger dude. But you could also change friction by changing mu, alright? And that doesn't have to do with the weight of the object, it has to do with the materials, changing the materials. Alright, so take the same truck, alright? Give yourself that little drawing of the truck. And instead of adding concrete to it, you know, that would increase the normal force on it. What we're going to do is we're going to take some steel chains to the tires. So now the surfaces in contact are different. It's just not rubber on snow, it's rubber and metal on snow. Rubber and metal on snow now. Right? So what we did by adding steel chains to the tires is we said, take mu and give me a higher mu, give me better materials in contact. We didn't increase Fn because we didn't increase the weight of the truck. But when mu goes up, you're going to get more friction, right? So if you add these, you know, steel chains here, mu goes up. By the equation, friction goes up as well, you know. Now what I want you to do is just write down, this is for you, you do this, write down an example of each. one example of changing friction, increasing or decreasing it by increasing or decreasing Fn. And think of one on your own also of changing friction by changing mu. Alright, and you could see with me if you came up with a good example. Alright, last thing we want to talk about is static and kinetic friction. So static friction acts when two surfaces are locked together and will not slide. Alright, think Velcro. So when Velcro is locked together and you can't slide it left to right, kind of like that, and you can't slide it. It's like, they're locked, right? That's static friction. Kinetic friction acts once things start sliding. Okay, kinetic friction is also called sliding friction. It's like a nickname for it. All right. So static friction. So if I take this object right here and I just put it on the page and I push on it, but it won't budge, right? So then it won't budge at all. It means the surfaces are locked together. It's static. It's staying still. That's what static means. So that's when you see static friction. But once I budge it and I'm sliding it now, hear that? That's when kinetic friction is acting on the object because it's sliding already. One thing is that FFS, force of friction, static. It's always harder. Think about it when you push on something. Is it harder to budge it or to keep it moving? Static friction is always stronger than kinetic because it's always harder to budge something than to keep it moving. All right. Now, I want you to think of your own examples right now, and you can see with me if you're right. Think of one example of a situation where static friction acts and write it down, and one example where kinetic friction acts. I gave you my example with the block, but you think of your own.